So where we're at, last week we did a little bit of practice with first order differential equations, and we've been doing a lot with first order differential equations. And the punchline is, when it comes to first order differential equations, we've got options. There's lots of things we can do. We're shifting over to higher order differential equations, and we're going to see that there's a lot fewer options. At least there's a lot fewer things we're going to talk about. And in particular, we're going to really narrow our focus to one particular type of differential equation. And in some sense, when it comes to higher order differential equations, there's basically just one thing we can do, which is good. That means we only have to master one technique. Of course, there's more to it than that, but we'll get there. So in general, what do we have? So what we start with is just a bunch of terminology, just so we make sure we understand what we're talking about. So in nth order differential equation, in particular nth order linear, so from now on we're really going to focus on linear. It's something which you can write in the following way. So you have the nth derivative, so nth order refers to the order of the highest derivative, so that's where this n shows up. And let's assume we have a 1 there. Plus, then there's some function of x, and this could be a really terrible function of x, but only of x. Then the n minus first derivative, and then n minus second, and so forth and so on, down to the first derivative times some function times to just the function y times some again function times on the other, well, equals on the other side some f of x. So anything which depends on x can be as bad as you want to write it. But when it comes to the y parts, they're very nice and organized. It's the y and some derivatives, and they're all arranged in a nice, what we call linear combinations, which means you take scaling factors, which are these functions that you see, the a sub I of x, and you add together. Now, a couple of terms. We often care about what happens on this right-hand side, so this f of x. And we split into two cases. So one case is if f of x equals 0. In some sense, that's our preferred case. Lots of good things happen when f of x equals 0. And we will call that homogeneous. Now you might say, haven't we seen that phrase before in a completely different context? Yes. Unfortunately, math ran into problems, and that they started running out of good terminology, so they began to recycle. So when we talk about a homogeneous or homogeneous differential equation, we basically mean that this right-hand side is 0. That's what we mean. If it's non-zero, we say it's non-homogeneous. And we'll eventually talk about things as well. We'll also talk about constant coefficients. And that just means that these functions up here are all fixed values. So, 2, 3, they don't depend on x. So that's what we mean. The f of x can still be arbitrary. So it can be some exotic function like sine of x or something. Okay, so those are some terminologies. So we'll talk about, we want an nth order linear homogeneous constant coefficient differential equation. It's like, oh yeah, I know what those things mean. Some facts. Do there exist solutions? And the answer is yes. So if we have a nice linear ordinary differential equations and we feed in some initial values, and you'll notice that our initial values all are at the same point. So in other words, we are looking at what's happening at the point A. So we say what's the function at A, what's the derivative at A, all the way up to the n minus first derivative at A. So we're just saying at this particular point, we understand what's happening. And then we say, and look, I can tell you what the nth derivative does. So if we combine these two things together, then there's a unique solution. And the unique solution basically works up until we run into problems. So problems would be where we have some things like discontinuities or asymptotes among our various pieces that are making up our differential equation. Another nice thing, and this will become so automatic, we won't even have to think about it very much, is this notion of superposition. Now, another way to think about superposition is I like to think of this as stacking. And what we have is in some special cases, in particular, when we're in the homogeneous case. So you see how we equal 0, that means we're homogeneous. So if we have a linear differential equation, which is homogeneous, so that's the two things we need, linear plus homogeneous. Then what we can do is if we have solutions, we can combine them together in nice ways and make new solutions. And the nice way is what we would call a linear combination. So in other words, if I have a collection of solutions, then I can multiply the first one by any arbitrary number, the second one by some other arbitrary number, and so forth and so on, and add them up, and I'll have a new solution. So we have this way of saying, oh, so instead of having to say, how do we find the right solution, we say, oh, let's find sort of a good family of solutions, and then all solutions should come from that. And in fact, that's the punchline. In particular, we say, look, if we have n solutions, and I want to say that n is very important here, that this n matches with that n. So we have n solutions, and they're linearly independent. Now, we'll talk about what that means in a little bit, but you should think linearly independent means essentially distinct. That you're really getting something from every single one. There's no like wasted solutions. Then all solutions have this form of this sort of superposition of putting them together. And so that's why we actually really like these homogeneous linear differential equations, because we know what we have to do. We say, look, we just have to find our family of nice linearly independent solutions, and then we know how to make all possible solutions. And of course, well, what if I want a particular solution? Well, you just say, well, find the right choice of CI that gives it to you. All right, so that's sort of some idea. I do want to talk a little bit about why superposition works, because it's such a really cool thing, and it really reinforces this notion of like, oh, linear is good. Linear is wonderful. So there's, just warning you, there's a lot here. Don't feel like you have to write this down. But I just want to show you how it works. Because like I said, there's a wall of text here. The wall of text is not the important thing. It says, look, suppose you have solutions. So what does that mean? It means when you plug it in, it works. So that's what it means, that y1 is a solution. It says, hey, y1 works. y2 is a solution. Y2 works. Okay. And then what you do is say, look, plug in C1, Y1 plus C2, Y2. Now, the nice thing that really makes all of this work is in the background, we're taking derivatives. So why is that important? Well, differentiation respects addition and respects multiplying by numbers. So in other words, differentiation is linear. So if I want to take the nth derivative of c1 times y1 plus c2 times y2, that's c1 times the nth derivative of y1 and c2 times the nth derivative of y2. And that's true for all of these terms here. And now, what do? Well, you say, look, I'll gather everything which has a c1. So this term has a c1, this term has a c1, don't forget, of course, that, all the way down to the end. So that I have a c1, there's a y1 to the n, here there's an a n minus 1x, y1 to the n minus 1, all the way down to a0x times y1. And then, look, great, do the same thing, but do it with c2. What happens? Well, you got a c2, y2 there, you got a c2, y2 there, don't forget, multiply in, so forth and so on, all the way to the end. And if you grab it out, what do you have? Well, you have c2, nth derivative of y2, a n minus 1 times the nth derivative, n minus first derivative of y2, all the way down to the end. And so you can rearrange, and you say, but wait, look, this is wonderful. Because what do you see? Here, we know it's a solution. So this part has to equal 0. And up here, this is a solution. So that part has to equal 0. And you get C1 times 0 plus C2 times 0 equals 0. Beautiful, beautiful. So really, there's a couple of nice things, linear, and the fact that if you add 0 to 0, you get 0. And if you multiply something by 0, you get 0. Now, here's another way to sort of think about the process. So let's suppose for a second here, let's just sort of call this part right here, call it the left-hand side. So I can think about it. You give me a function y, I can throw it into that left-hand side. I can see what comes out. So if we do that, here's sort of the punchline. Because it's linear, what happens is if you were to put in something of the form that has C1 y1 plus C2 y2, what linear really says is the following. Namely, that says, look, this is really C1 when you plug in. I should not try to draw this in real time, should I? All right, imagine I could draw quickly and accurately. Well, You're all looking at me drawing boxes and like, I appreciate you being patient. Thank you. Okay, so the punchline here is that when you have something linear, you always have this diagram. Namely, that you say, look, if I want to plug in C1 y1 plus C2 y2, then what I can really do is I can think about it as saying, look, I just have to plug in the y1, and whatever comes out, I multiply by C1. And I plug in the y2, and whatever comes out, I multiply by C2. And now, since we have solutions, these parts equal 0, and therefore the whole thing equals 0. So that's sort of what goes on because of linearity. And we'll see this picture again, probably drawn a little bit better later on. All right, so those are our basics. And now we're ready to get into some practice. All right. Verify. So we should just do a quick reminder of what it means to verify. Verify that e to the x and x e to the x are solutions to y double prime minus 2y prime plus y equals 0. And find the solution to y, which satisfies y of 0 equals something, and y prime is 0 equals something. Now, of course, audience participation. What do you want y of 0 to be? Give me a value. Pi. I'm not worried about this. I can solve it, no worries. Y prime is 0. What do you want that to be? 18. Okay, that was... Now, don't worry. This is not going to be bad. Okay, so there's a couple things. There's two parts. There's the verify, and then there's the find the solution. So let's just remind ourselves of verifying. So to verify basically says what? Well, you plug in e to the x into the left-hand side. And after you plug e to the x into the left-hand side, you say, does it equal the right-hand side? You're plugging in, just like we had our little machine just a few minutes ago. All right, so let's start with e to the x. Let's remind ourselves, what's the derivative of e to the x? Yeah, I asked, what's the derivative of e to the... Oh, wait, no. I see what you did there. And y double prime? E to the x. So y double prime minus 2y prime plus y would become e to the x minus 2 times e to the x plus e to the x. Well, what happens when you put those together? It equals 0. Wow. Who knew? Well, they knew, because they said verify, because it must be true. They wouldn't ask us to verify something that wasn't true, would they? Not intentionally, I hope. All right, next one. X e to the x. Okay, what does y prime look like? A little bit slower here. Sorry, what? E to the x plus x e to the x. That's a beautiful answer. And where did that come from? Product rule. Yeah. Two functions multiplying. That means that we're taking a product of two functions. We can do a product rule. We can also write this as x plus 1 e to the x if we wanted to. What's y double prime? All right, so you can apply, we know the derivative of x e to the x, so it's x e to the x plus e to the x. We know the derivative of e to the x is e to the x. So there's x e to the x plus 2 e to the x, which we could write as x plus 2 e to the x. Okay, so y double prime minus 2y prime plus y would equal, make sure you grab the right terms, x plus 2 e to the x, that's the y double prime, minus 2 times x plus 1 e to the x, and then plus x e to the x. What does it simplify to? Well, maybe that's not quite so fast, but we can, of course, expand everything out. And if you do that, you will get what's written here. How many x e to the x's do we have? None of them. Yeah, they all cancel. How many e to the x's do we have? 0. So altogether, what do we have? 0. So now we've verified it. Okay, so that's the first part. So the verifying is done. Now, find the solution. Now you might say, well, great, we have two solutions. Is e to the x, does that work with these initial conditions? So like, does e to the 0 equal pi and e prime to 0 equal 18? No. So it's not that one. No problem. We have a second one. What about x e to the x? Does that satisfy the conditions? No. Dang it. Gah. So what are we going to do?
Drop question.
Drop a question? No, no, no. We're going to get all the points. That's our goal, all the points. Got to get them all. Is there anything that we've learned about that's nice when it comes to things which are linear and homogeneous? Anything at all? Anything? Anything? Is there something we've learned about that might be useful to help us solve this problem? Can't think of it. Let's keep thinking harder. I think if we think harder, we'll find something that could help. There might be a tool available to us, something that if we used could help us solve this problem. Is there anything that jumps out as an idea that we could use here? Yeah, stacking. Right. Good. You got it. So the punchline here is once we have two solutions, we actually don't have two solutions. We have this beautiful array of solutions. So we now know, hey, I can write solutions in the following way. Some constant e to the x plus some constant x e to the x. So in other words, combine our solutions to make a bigger family. And a and b can be arbitrary. And notice I have two choices here. I have a choice for a and a choice for b. And I want two things to be true. It's like the stars have aligned. Okay, so let's see. We want something about y. We also want something about y prime. So let's write down y prime here. What's the derivative of a times e to the x? Yeah, a times e to the x. The derivative of b times x e to the x. Yeah, see, we can just copy here. We don't have to do anything creative. Okay, so now what we'll do is we'll plug in y of 0, and let's see what it tells us. Well, y of 0, we want it to be pi. But here, when we plug in 0, what do we get? You'll get A, and e to 0 is 1, and then this part? 0. What about y prime of 0? Well, that should be 18. What is it equal to here? A n plus b. Right? Because you plug in 0, 0 plus 1 is 1 times e to 0. Okay, so now I have two equations I have to solve for a and b. Well, I think one of them is pretty easy to solve for. What's a? Yeah, you got that one. What's b? 18 minus pi, because right, we know a is pi, put it in. So we say perfect. So therefore, the solution is pi e to the x plus 18 minus pi x e to the x. And that satisfies our initial conditions. And life is good. So it's great. It's like if we have solutions, we can combine them and make new solutions. You get that? Are you good? All right. Well, let's find out. So given that x squared and 1 over x cubed are solutions to x squared y double prime plus 2xy prime minus 6y equals 0, then find the solution y which satisfies y of 2 equals 10 and y prime of 2 equals 15. There's no need to verify. We're just looking for a new solution. So the key here is we're told there are solutions. It's probably not one of these, but because we have solutions, we can say, look, we can combine these together to get a bigger family of solutions. ax squared plus b times 1 over x cubed. And now we plug in. Now notice here, we're not plugging in at 0, so pay attention. Not everything happens at 0. There are other numbers out there. We like 0, but sometimes other numbers exist. We should refer to y prime, so that's 2ax. What's this derivative? Derivative of 1 over x cubed? So, yeah, so x cubed downstairs is x to the minus 3 power. The minus 3 comes down, so you have a minus 3b, x to minus 4, which is 1 over x to the 4th. All right, so we plug in our numbers. Y of 2, well, that would be 4a plus 1 over 8b, because 2 squared is 4, 2 cubed is 8. Y prime of 2, oh, this equals, by the way, 10. Y prime of 2 would be, plug it here. So, well, turns out still 4a. And then here, 2 to the 4th is 16, so that's minus 3 over 16. B equals 15. All right. So, what will happen, and this will always happen, is once we have our solutions and take their combination, stack them, superposition, whatever you want to call it, then when we're solving for initial conditions, we're going to get a system of equations where we have, like 2 equations, 2 unknowns, or maybe 3 equations, 3 unknowns, or 17 equations, 17 unknowns. Usually we use a computer for that one. So we have to solve. So then the question is, well, how do you solve? Now, last time we did it, the previous problem was like, super easy. There was a freebie. This one, there's not a freebie. So what are some techniques for solving things like this? Okay, so there's 2 things that people mention. One of them is substitution, which is like solve for one variable in one equation and plug it into the other equation. That eliminates a variable. The other thing that people mention is elimination. Now, you may not have used the word substitution or elimination, but that's the idea. So elimination says, let's combine these equations in such a way that we knock out something. Now, they both have the same flavor. It says, I want to get it simpler. So I don't want 2 equations with 2 unknowns. I want 1 equation with 1 unknown, because that we can handle. So substitution works, but I prefer elimination. And so in particular, is there a nice way to combine these equations so that we can cancel something out? Yeah, so what we can do, so what we are referring to here, in case it's been a while, is we can multiply one equation by some number. And so let's say I multiply the top equation by a +1 and the bottom equation by a -1, and then we add the results. So this is the same as subtracting. Of course, things can get more delicate when constants get weirder. So if I had a 4a and a negative 4a, what's the result?
0.
Yeah, no a. It goes away. Like, woohoo, yay, we got rid of it. Now, hopefully we have something left. Otherwise, it's not very good. But let's see. We have 1 over 8. Then we're going to add, because like minus minus makes add, 3 over 16. 1 over 8 plus 3 over 16, also known as? Yeah, also known as, we do a work on the side here, because we can't do math in our head. 1 over 8, common denominator would be 2 over 16, and 3 over 16. Ah, yes, it is 5 over 6. You guys are good. Okay, 10 minus 5 is? Yeah, so positive 10 minus 15 minus 5. So, okay, so move the 16 over 5 across by multiplying by the reciprocal. And that tells us, lo and behold, b equals negative 16. Yes, that's good. Now, once you know b, how do you get a? Yeah, plug it back in. Now, which one do I have to plug it back into? It doesn't matter, right? As long as it's something with a, you'll make progress. Oh, I like the top one because it looks simpler. So 4a plus 1/8 times negative 16 equals 10. Well, 1/8 times negative 16, negative 2. So when we move it across, 4a would equal, 12, because it's negative 2, so we'd add 2. So a would be 3, which means that, yes, there we go. There's the solution that we need. And life is good. All right, so that's where superposition comes into play. If you have some solutions, you have a whole family of solutions, and you can find the right one that you need. Or you could say, look, here's my family of solutions. So, back to an earlier thing. We talked about a word. So we're going to spend a little bit of time here. Linearly independent. And there's some technical things. Now, if you've had linear algebra before, this might seem familiar. And if you haven't had linear algebra before, maybe it's not so familiar. But I don't want you to get hung up on the details. So I like to think in our setting, linearly independent says, hey, you're getting something useful out. So to make this more concrete for our discussion, so suppose we have something, and I say, if I have C1, well, suppose I have A times X, and I have B times 2X. So in other words, I can think of like, look, X and 2X were both solutions. Well, what could you do here? You could rewrite this, right? Because you could say, factor in X, that's like the same as A plus 2B times X. But what's this? It's a constant. So actually, even though up here it looks like I have 2 choices, I secretly only have 1. So I sort of have a collapse. Because 2x is really nothing, I don't get anything new. Once I have x, 2x doesn't add anything new. And of course, you can do more complicated things. You could say, well, suppose I have, a times x and b times x plus 3 and c times 2x minus 4. Well, what could I do here? Yeah, someone says rewrite it. I think that's a great way to think about it. So the constant would be 3b minus 4c plus, and then we have here, I'll just grab the stuff with x, a plus b plus 2c times x. And then we say, well, look, really, I don't have 3 constants. These collapse. I have 2 constants. So what we'd like to do is we'd like to say, look, I want to make sure I don't have redundancies. That's what we're after. That's what we're after. And so that's what this is getting into when it says linearly independent. If the only way I can combine things and get 0 is, in fact, everything had to be 0. So when you have things like this going on, things don't have to be 0. For example, I could take, a to be minus 2 and b to be plus 1. And then I'd get 0 out without having them both be 0. So linearly independent, our idea here is linearly independent is really just a stand-in for saying all of my solutions are actually meaningful. I'm getting something from each solution. Okay, so how do we do that? So we have a tool. It's called the Wronskian. So how does the Wronskian work? Well, it says you have your collection of functions, and you set up a matrix. So for example, if you have 2 functions, the first row is your functions, y1, y2, and your second row is your derivatives, y1 prime, y2 prime. And after you set up your matrix, there's something called the determinant, which is, it says, I don't want a matrix, I actually just want a single quantity, in this case a function. Now, for a 2 by 2 matrix, the rule is you go up one way and you go down the other way. And the rule is you add the stuff in the down diagonal, so that's the y1, y2 prime, subtract what you had in the up diagonal. So this is the Wronskian of 2 functions. Now, if we have more functions, things get more interesting. But it's the same idea. So if I have k functions, the first row, those are my k functions. And then below it, I put my derivatives. And then below that, the second derivatives, and then the third derivatives. And I just keep going until I get something that's a nice square matrix. And I take that determinant. And so the result is a function. So the output is always a function. And what we say is, well, what does that function tell us? And there's a nice fact. If these functions are linearly dependent, in other words, there's redundancies, they're not useful, then the Wronskian has to be 0. So we don't like linearly dependent, we want linearly independent, we want the opposite. So that's where the second fact. If they're linearly independent, then the Wronskian is non-zero. And so we say, good. So this is what we're looking for. As long as the Wronskian is not 0, that says, lo and behold, the solutions are distinct. We're getting something from each function. There's no redundancies. So there we go. Now there is a little parenthetical comment which we'll come back to. It says, well, you might have a Wronskian which is sometimes 0, but usually not 0. Well, what does that mean? We'll talk about that in just a few minutes. But let's do a quick example, because we should do a quick example. All right, compute the Wronskian for sine x and cosine x. So we're saying, all right, the Wronskian for sine x, cosine x. What we do is we set up a matrix. The top row are the functions, sine x, cosine x. The next row are the derivatives. So what's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. And now we take the determinant. So going down first, sine times negative sine would give us negative sine squared, and we add the negative sine squared. Then we go up, which would give us cosine squared, and we subtract that. Well, negative sine squared x minus cosine squared x, is there another way to write that? -1. Now, what do we know about negative 1? It's not equal 0. Which means that these are linearly independent. We get something from having them both. There's no redundancy built in. So that's a good thing to do. All right. So the key ideas: define the Wronskian, set up our matrix. Functions in the first row, first derivatives in the second row, so forth and so on. Take the Wronskian and ask the question, 0 or non-zero. Non-zero is the good one. We want non-zero. All right, are you ready to try one? Yes? No? All right, compute the Wronskian for x e to the x and e to the negative x. When we're doing the Wronskian, what do? Well, we set up a matrix. We fill it in. The first row is just copying. We don't even have to think about this. This is the great thing. Not that we don't think, but just sort of like the process works itself. All right, we'll start with the derivative of e to the negative x, as that probably is quicker. Derivative of e to the negative x? Negative e to the negative x. Derivative of x e to the x. X plus 1 e to the x. We know that because we did it earlier. Exactly. Haha, we recycled. Good for us. We're environmental. All right. So now there's two things we have to multiply, right? So we go downhill, and that would be x e to the x times negative e to the negative x. That's going down. Subtract, going up. X plus 1 e to the x times e to the negative x. Now, if you multiply e to the x by e to the negative x, what do you get? 1. So lo and behold, these will end up sort of canceling out in some sense. And so we have negative x minus x minus 1, which is minus 2x minus 1. Aha! Good. So there we go. There we go. Now, things can happen like if you forgot a minus sign. That might be a reason why your x's canceled out. Now, quick question. Are these linearly independent? Yes? Except for... So this is not equal 0, except there is one time when it does equal 0. Do you see it? Negative a half. Now you might say, well, what does that mean? What does that mean? Well, the answer is now, in terms of the differential equation, we don't have a differential equation. But if there were one, what this would mean, we would say, if you have a solution above negative a half, you can only push it to negative a half. Essentially, negative a half is where your differential equation breaks down. So this would be your differential equation breaks down point. So away from negative half, life is good. At negative half, things break down. So that's just a side note. Now I have some time, which means examples, more examples. And we're going to build on this a lot come Friday. So there's something called constant coefficient. We talked about it earlier. It just means your coefficients are constants. And constant coefficient plus linear plus homogeneous, it's like our dream differential equation. It's like, I really hope I'm getting a constant coefficient, homogeneous, linear differential equation. Because what happens? Well, it's actually things that we've seen before. So if my differential equation looks like ay double prime plus by prime plus cy equals 0. So again, see, it's linear, it's constant coefficient, it's homogeneous. We did this a long time ago, right at the very start. Like week 1 stuff. We said, hey, what if I think of my solution as e to the rx? What would that do? Well, what it does is it transforms and says, well, this will work if r is a root of ar squared plus br plus c equals 0. Because what happens is every time you take a derivative, an r comes down. Take 2 derivatives, 2 r's come down. So that's why there's an r squared. And see how easy it is to jump back and forth? It's like, however many derivatives, that's power of r. 2 derivatives, r squared. 1 derivative, r. No derivatives, no r. So we can jump back and forth. So we say, okay, great, find the roots. Now, if the roots are not the same, then they're linearly independent. We'll just take that as a fact. And so we say, look, here's a beautiful set of solutions. If the roots are the same, well, we run into a small problem. I can't just use, constant 1 times my first root plus constant 2 times my second root, right? E to the Rx, e to the Rx. I somehow have to distinguish the second function. And the way you distinguish is you nudge it. So there's a little nudge factor of x right there. That helps get you something which works. Now, you might say, wait, is it really there? If you think back to our example, our first example, where we had, check that e to the x and x e to the x are solutions. That's an example where, the x comes into play. All right, so we have enough time to solve one of these. Let's solve this one. So how does it work? Well, what's the polynomial I need to solve?
2r squared
2r squared
minus 7r
minus 7r
plus 3 equals 0.
plus 3 equals 0. All right, polynomial. You have to solve it. What do? You factor. Well, you knock on wood and hope it does factor. Does it factor? Well, if it did, you'd need to have a 2r and a 3, because you got to get up to 6r. I think a 1 and an r. Does that work? 2r minus 1r minus 3? I don't know. 2r squared minus 6r minus r. Ooh. Plus, yes! Ha-ha! Woohoo! Okay, so what are the roots? 1/2 and 3. They're not the same. So, great. We're in this case. So that says, look, our solutions look like some constant. I can just use a, I don't have to use C1. E to the 1/2 x plus some constant e to the 3x. We have should we do this one really quick? Yeah, let's finish it. We're completist. All right. That is, we want to complete stuff. So, 9r squared minus 12r plus 4 equals 0. Does this factor? I write it like it does factor. Three r minus 2, 3r minus 2. You should be suspicious. He has 2 dots. He has 2 examples. He's already used 1 dot. Must be the other dot. Okay. So 3/2, 2/3, 2/3. I know how to do math. I've been doing it a long time. I make mistakes copying, but I know how to do it. All right. So what does the solution look like? Well, it's repeated roots. So now we're in this case. So some constant e to the 2/3 x plus some other constant times x e to the 2/3 x. All right. We'll stop here.